Okay, this video is covering questions 11 through 20, the ones that were requested. So it is estimated that 20% of all drivers do not signal when changing lanes. In a random sample of 4 drivers, what's the probability that at least one doesn't signal when changing lanes? So we have a probability that is not changing, and we have a fixed number of trials. So this means we're working with a binomial. All right, and basically we can have 0, 1, 2, 3, or 4. And so they ask for probability at least 1. So essentially this is going to be the PDF of 1 plus the PDF of 2 plus the PDF of 3 plus the PDF of 4. All right, and when you go through this, so my work shown is going to look like this. 4 choose 1, 0.2 to the first, 0.8 cubed plus dot 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 plus 4 choose 4, 0.2 to the fourth, 0.8 to the 0. This would be the probability that all 4 of them didn't. So this would be if I was showing work on a test. Okay. All right. So real quickly, I can look at this and go, well, you know what? It doesn't look like much of any of these. But since it's the least, we can sit there and go, well, it's 1 minus the binom CDF of 0. All right. Which, since it's only a singular value, is going to be 1 minus 4 choose 0, 0.2 to the 0, 0.8 to the fourth. 4 choose 0 is 1, 0.2 to the 0 is 1. So this part goes away, and here's all I have left. All right. Now, if you didn't remember that part of things, you can actually go through, plug all these into the calculator, and do this just like this. 1 minus binom CDF, trials is 4, probabilities 0.2, x is 0. And if I had done that, I would have gotten this response as long as I had to go back and check all of those. Okay, I recognize that's a bit of work, but it will satisfy. It is estimated that, this is number 12, it's estimated that 30% of all cars parked in the metered lot outside City Hall receive tickets for the meter violations. In a random sample of 5 cars, what's the probability that at least one receives a parking ticket? This can also be done using classical probability, but I'm going to, since this, and there's nothing wrong with it. And by the way, on the test, if there's something on a test or quiz that you can use classical probability instead of using a binomial or geometric, that's perfectly acceptable. I'm going to approach this from the binomial standpoint because it's what we're studying now, but there's nothing wrong with using the binomial, using classical probability to solve this type of problem. So if you prefer that, that is absolutely fine. So we have random sample 5 cars in a lot. So we have a specific number of trials, which in this case is 5, 0, 1, 2, 3, 4, 5. We want the probability of at least 1. So it means we want 1 minus the probability of 0. All right, at which point you can take that and solve it using the classical probability, using the binomial. Using the binomial, you would have done this. We have 5, choose 1, because the PDF of 1 plus the PDF of 2 plus the PDF of 3. 5, choose 1. The probability was 0.3 to the first power. 5 minus 1 is 4. Plus dot 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 plus 5, choose 5, 0.3 to the fifth, 0.7 to the 0. All right, so that would be the way if I actually had to calculate it out using the binomial, but using, if it were multiple choice and this is actually checking my work, 1 minus binom CDF, which in this case, 5 trials, probability is 0.3, and X value of 0. And what was done here for the classical probability, 1 minus, how should I say this? One minus, we needed the probability of 0, which means 0.3 to the 0, 0.7 to the 5th. All right. That, of course, is 1, 0, and so once again, we get here. So whether you do this through by a classical probability or through the binomial situation, that's fine. Okay. But classical is probably actually easier, but I know some students struggle with that, which is why we also have the binomial. We teach the binomial as a backup. Once again, on problems 11, 12, and 13, you can do these using classical probability, but we recognize this is something students struggle with. So we're trying to give them a calculator backup to use the binomial because quite frankly, they tend to do well with that. But if you can do it using classical probability, it's definitely faster. Okay, definitely faster. All right. So according to one poll, 12% of the public favor legalizing drugs in a simple random sample of 6. So we have a fixed number of trials, a fixed probability. So I can look at this as a binomial. What's the probability of at least 1? As soon as I see at least, I always think 1 minus. In this case, 0, 1, 2, 3, 4, 5, 6. At least 1 means 1 minus the probability of 0. So if I'm showing work and if I'm approaching this from a binomial standpoint, I need to go the PDF of 1, which is 6 choose 1, 0.12 to the first power, 0.88 to the 5th, plus dot 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 plus 6 choose 6, 0.12 to the 6th power, 0.88 to the 0. Calculator work, 1 minus binom CDF, probability trials is 6, probability is 0.12, X value is 0. This equates to 1 minus we basically need, this equates to 1 minus 6 choose 0, 0.12 to the 0, 0.88 to the 6. This part becomes 1, and we have 1 minus 0.88 to the 6th power. Okay, 1 minus 0.88 to the 6th power. All right, so number 14, you win a game if you flip a coin with heads coming up exactly 50% of the tosses. Would you rather flip 10 times or 100 times? Well, the immediate thought through your mind typically is law of large numbers gets me closer and closer to reality. And that's true. However, this is a binomial. So we're not looking for close, we're looking for a specific 50%. And so let's run 2 binomials and see what happens. So we have 10 choose 5, 0.5, because the probability of getting it to heads is 0.5. And then we're going to do the same thing. 100, choose 50. 0.5 to the 50, 0.5 to the 50. So we're going to do the binomial for both of these and take a look at it. All right, we're going to take the binomial for both of these and take a look at it. Now, this is the case because they're looking for exactly 50%. Okay, so second bars, binomial PDF, trials is 10, probability 0.5, x value 5. And we find out we get 0.246 for this one. So if we flip it 10 times, about 24% of the time, we end up with exactly 50%. In other words, the rest of the time, we're going to end up with 6. It happens 6 or 7 or 4 or 3 times. Now we're going to do the same thing with flipping it 100 times. So binomial PDF, trials are 100, probability of success is 0.5, but now we need it to happen exactly 50 times. And we end up finding out that it's 0.0795, which is less than that. So consequently, we'd rather flip it 10 times than 100 times. And you go, well, wait a second, it doesn't match law of numbers. Law of numbers is not the individual time. It's on average. The average will get closer. Remember, law of large numbers is talking about the average getting closer to reality, not any one specific time. So great question came up in the chat. How did I know whether or not to, how did I know not to use law of large numbers and go directly to binomial? Well, it said exactly 50 times. So as soon as they said exactly, I go, you know what? I think you're trying to be tricky. And exact is a binomial PDF. Now, what clued me into why that might be important is because when I do law of large numbers, we're talking about in the long run or on average, we're not talking about any one time. So if I'm only flipping at one time, it could be, it's possible that I don't get that many heads or I get a lot more heads on any one time. So I need to look at it and go, on average, what's going to be my best bet if I'm using law of large numbers. So, if there are 100 of us doing it, law of large numbers said do it more times. But for any one person, or for any, if you're going to flip it a specific number of times, the minimum number of times is usually going to be your best bet because it's a binomial PDF. All right, 15 is a more challenging question. It costs $4 to play a game in which 3 fair coins are tossed. If all land heads, the player is paid $10, and if exactly 2 land heads, the player is paid $5. What is the player's expected outcome? All right, so here we have 0, 1, 2, 3. All right. If I get 2 heads, I get $5. If I get 3 heads, I get $10. But it cost me $4 to play the game. So in this case, I would expect to win $1. 5 minus 4 is 1. 10 minus 4 is 6. Here, I'm going to lose. All right. So here I'm going to lose $4. So when I go about playing this game, I can actually win with a binomial here. And the probability of this happening is 3 choose 2. 3 choose 2. Probability of a heads is 0.5. And 3 minus 2 is 1. So that gets me a win. So let's calculate that probability, please. So second vars, binomial, PDF. Trials is 3, probability is 0.5, X value is 2. So 0.375 chance. So there's a 0.375 chance of this happening. On the other side, 3 choose 3, 0.5, and let's figure that one out. Second vars, binomial PDF is changing my X value to 3. And the probability of that happening is 0.125. Well, when I add these up, if I were to add these two values up, so this is the probability of winning $1. This is a probability of winning $10. But if I add that up, that means there's 0.5. So these, the probability that I lose $4 is 50%. So my actual expected value is going to be this, 0.5 times a negative 4 plus 0.375 times 1 plus 0.125 times 10. So let's add that up. Let's do the calculation. All right. So 0.5 times negative 4. Oops, I should type 0.5 times negative 4 plus 0.375 times 1 plus 0.125 times 10.
Wouldn't it be multiplied by 6 rather than 10? Since that's the dollar value?
Yes, yes, it would be. Thank you so much. Yeah, they caught me on this. This 6, I should have brought this 6 over. This 6 goes right here. Thank you so much for catching me on that. 0.5 times negative 4 plus 0.375 times 1 plus 0.125 times 6. So I end up losing 80.875. Now, so I plan to lose 0.875. This is what I'm losing, but I'm playing this thing 4 times. So negative 0.875 times 4. So negative 350. So if I play this thing over and over again, in other words, 4 times, I expect to lose $3.50. Pause the recording. All right, so suppose we have random variable x where k equals 0, 1, k equals 0 through 12, the associated probabilities. And here is my equation, and we're missing some things, but it says, what is the mean of x? Well, remember, the mean of the binomial, or the expected value of the binomial, is NP. All right, our number of trials is 12. Our probability is 0.34. Okay, so that's the way you would work number 16. Number 17 was what was asked for. Suppose we have a binomial random variable where the probability of exactly 4 successes is this. What is the mean of the distribution? Well, the problem here is I don't see immediately how many trials there are. But the number of trials is the sum of my exponents. So 4 plus 7 equals 11. So this is actually 11 choose 4. And then we also don't have the probability, but the probability is 1 minus Q. So in this case, probability is 1 minus 0.37. So the probability is 0.63. So in this case, 0.6, I should write this down here, 11, choose 4, 0.63 to the fourth, 0.37 to the seventh power. Anyway, for the expected value, now that I have all that information, the expected value is going to be 11 times 0.63, right? 11 times 0.63. And that gives us 6.93. So the question is, on 16 and 17, it asks for mean. Why did I solve for the expected value? Mean is another term for average, and it also is expected value. They're not 100% synonymous, but they're really, really close. So when they ask you to solve for that, they're asking for what's the expected value, because the expected value is what you expect to happen on average. On average, this is what we expect. And so, we're asking for the average, so we're asking for the mean. So those are pretty much interchangeable terms. Looking at number 18, for which of the following is a binomial an appropriate model? So basically what they're asking for is, hey, what are the constraints for a binomial? And the constraints for a binomial are these. You need to have a Bernoulli trial. Well, Bernoulli trial means you need a yes or no situation. Your probabilities need to be constant, and each one needs to be, in each trial needs to be independent or not impacted by all of them. So the number of heads and 10 coin tosses of an unfair coin weighted so that heads comes up twice as often as tails. Well, in this particular case, the coin has been altered, but so heads is essentially coming up 2/3, tails is essentially coming up 1/3, but that's a fixed probability, and we also have a fixed number of trials, so this looks pretty good. The number of hits in 5 at-bats where the probability of a hitter is either 0.352 or 0.324. Our probability is not constant, so this is a bad choice. The number of tosses of a fair coin before heads appear on 2 consecutive tosses. Okay, so the number of tosses wasn't defined. We need it to be a specific number of trials. If they said the number of heads on 5 tosses or the number of heads on 2 tosses, that's fine, but the number of trials was not fixed, so this doesn't work. The number of snowy days in a given week, obviously that changes. So consequently, that's not a fixed probability, and quite frankly, it's not independent, because if it snowed one day, it's more likely to snow the next day than otherwise. Well, how do you know that, Mr. Spencer? It's like, well, just thinking about this, if it snowed, that probably means it's winter, which means I have a better chance of it snowing than, it was sunny, which might mean it was summer, which is going to have a very low chance of snowing. So consequently, the probabilities aren't the same. So B is no good. So we're looking for the definition of Bernoulli. Bernoulli is a Bernoulli in a binomial, fixed number of trials, fixed probability, and each trial is independent of the others. All right, question number 19. All of the following statements are true for all discrete random variables except for which one? The possible outcomes must all be numerical. That is true. Discrete random variables, we're looking for numerical values. Matter of fact, they need to be whole numbers, 1, 2, 3, 4, 0, etc. The possible outcomes must be mutually exclusive. This is also a true statement. In other words, when it can't be both things at the same time. So if I'm rolling a dice, I can either get a 1 or I can get a 2, but I can't get both at the same time. The mean always equals the sum of the products. Yes, this is basically the expected value computation, where it's the probability times the numerical value plus the probability times the numerical, etc. That's also true. Standard deviations can never be negative. That's always true. Standard deviations can never be negative. The next one, approximately 95% of the outcomes will be within 2 standard deviations of the mean. This is true only for the normal. This is true only for the normal. That's reference to the empirical rule. And the empirical rule says about 95% will be within 2 standard deviations. But that's only true for the normal. And they said they wanted this to be true for all discrete random variables. All right, it needed to be true for all discrete random variables. So that is true for the normal, which is actually continuous. But aside from being a continuous, it's not. It's the empirical rule only applies to the normal, not to all discretes. All right. So which of the following is a binomial random variable? The number of tosses before a 5 appears. So this one says, hey, we're tossing and we're tossing until the first 5 appears. This makes this a geo. So this is a false. This is not a binomial. The number of points a hockey team receives in 10 games, where 2 points are awarded for wins, 1 point for ties, and no points for losses. Once again, we don't have a yes/no situation. We have 2 points and 1 point and 0 points, so it's not a yes/no. So this will not work. The number of hearts out of a 5 cards randomly drawn from a deck of 52 without replacement. Because of the without replacement, the probabilities are changing. Probabilities are changing, can't be binomial, has to not change. The number of motorists not wearing seat belts in a random sample of 5 drivers. Probabilities change per driver. Now, if you want to say that 20% of drivers aren't wearing seat belts, you'd be okay. But when you're talking about individual drivers, that's not a really good answer. This is not the best question. The answer is none of the above are good choices. The number of motorists not wearing seat belts in a random sample of 5 drivers also has one other issue with it, and that is there is they are not independent in that if one person isn't wearing a seatbelt, it's more likely that other people aren't wearing seatbelts. Generally speaking, seatbelts is related. If one person's wearing it, then almost everybody's wearing it. Whereas if one person is not wearing it, it's more likely that the rest are not wearing it. Okay, and so there is a dependency there. Not the best question. I promise the ones on the test will not be anything like